So the UI for assignment 2 is identical. There is very little different other than some of the options have changed a little bit. And so where you did BFS, DFS, and the grad students did IDDFS in assignment 1, now you will be implementing the A-star algorithm. But as we will find out very shortly, it's implementing A-star, as you've seen from the slides, is just a few lines of code different from BFS or DFS. It's essentially the same type of algorithm. You're just selecting the thing from the open list with the minimum F value. And so why this assignment is as much work as it is because there's a whole bunch of other cool optimizations and stuff that we're doing on top of that that will take up the majority of the time. And the way I like to do my assignments is that it's not necessarily that any of this is needlessly complex or complicated or difficult. There's just a lot of it, right? And so we're going to be doing a lot of programming in this assignment, working with a lot of arrays and stuff. So if your JavaScript is a little bit weak, you still should be fine, but just make sure you have enough time to do the assignment. All right, so up here, we've got the same options, all the same maps. We can toggle the grid on or off. I think I'm going to toggle the grid off because it just shows up on the projector a little bit nicer. For our search algorithms this time, we have student A-star and solution A-star. So of course, if I have student A-star selected and I click and drag, I get that same fake path that we had before. But when I choose solution A-star, I actually get a 8-directional path found by A-star, the A-star search algorithm. So that's in the solution. I will get into this option over here. So we see we have another option here, which is unidirectional or bidirectional. And I will get into what that is later in the lecture, but that is the differentiator this time between the undergrad version of the course and the grad version of the course. So the grad students will have to implement bidirectional A-star search, but the undergrad students won't. The next new thing here is that we have an object size. So before, our object was just size 1. So if I go into a smaller thing here and I just click a starting point, so we have a 1x1 object, I'll toggle on the grid, versus a 2x2 object versus a 3x3 object. And so the 3x3 will take up 9 cells on the grid, the 2x2 will take up 4, and then the 1x1 is what you're used to. So I'll go back over here to default, and I'll just show you that if I do click here, 2x2, you can see that now we are doing path finding for a 2x2 object. And it turns out that when you change the size of the object, now it is going to be running into certain obstacles that it wasn't before, when it was smaller. So if I select 3x3 here, you see now this object has to come around to the right of this thing rather than going to the left. Also, another example here is if I put the start here and the endpoint over here, then the object can go through this sort of really small maze here in the middle of this island. But if I select 2x2, then the object will now have to go up and around to get to that point. And so by changing the object size, you are changing the path finding, right? It can no longer fit. And if I select 3x3 here, well, there's no path possible, right? Because it can't physically fit there. Let's go back to 1x1. All right, so now we have another option here, which is legal actions. So now I can select the legal actions that my search is allowed to do. And by default, we have 8-directional movement. So this is up, down, left, and right, and each of the 4 diagonals. Or I can select the 4-directional movement, and your search algorithm should work regardless of which one is selected. So this is the optimal 4-directional path, and this is the optimal 8-directional path. Also, we have the heuristic function. So as we talked about last time with the A-star search algorithm, or 2 lectures ago, there is a heuristic function h of n, and that is the guess at how much distance we have left to go. And so we have this selector here for 4 different heuristic functions. So the heuristic function right now is 8-directional Manhattan distance. We also have 4-directional Manhattan distance. We have 2D Euclidean distance, and we also have 0. So as we looked last time, if we do A-star with the 0 heuristic, does anyone remember which algorithm we will be approximating if we do that? Yep. Uniform cost search. So if I do this, and I select 0, then, okay, let me come over to this blank one and animated search. So A star with a 0 heuristic, f equals g plus h. If h is 0, then f is just equal to g, so that's uniform cost search. So we just get this expanding the closest thing to the start node. Okay, so we have all of these options here this time for the search. Also down here, we are able to run the tests. So if I click run the test, you'll see here that all of the example ones are returning 964. The reason for that is just because I've taken all 8 of the directions and just added their costs together. So as an example, which we'll get to in the code, these all return 964. But if I change it to solution and click run tests, you can see that these tests are pretty quick. So it's running on my laptop in about 7 milliseconds. If I change this to bidirectional search, if you've done it correctly, the test should also pass. And here, the bidirectional is about twice the running time as the unidirectional. Now, the theory of bidirectional search says that it should be helping us, but in this case, we're doing a particular thing that will actually hurt us a little bit. But it's the algorithmic part of it that I care about, right? The fact that the tests are passing for both the solution, for the student one, for unidirectional, for the undergrads, and bidirectional as well for the grads. And I don't think I have... Oh, I do want to show a couple more things. So if I choose solution bidirectional, and then I click animated search, and I click here, then I click down here, you can see that it is expanding both from the start and from the goal. I'll get to that part of it when I get into the slides, but this is how we are going to be grading your assignment for bidirectional search to make sure that, yes, you are actually expanding from both directions. And here, if I do bidirectional search, for example, let's go to this 32 by 32. So if I click here and then click down here, what you'll see is, oh, that's not bidirectional at all. That's unidirectional. And it's because the way bidirectional search works is you're taking the minimum f value from both of the open lists, right? And because here, with A star, the f value with no obstacles is giving us the optimal path, then we're just taking, all of these nodes have the same f value. So what you can do to test your bidirectional search to make sure that it is actually taking things from both lists is to discard the heuristic completely by selecting the 0 heuristic. And then you'll see, okay, now we are taking them from both the open and the closed, from both open lists. And why is this different? Is because with 0 heuristic, it's just f equal to g. And so what it's doing, it is taking the closest thing to either of the starting locations. Okay, so that's why this is. And then you'll see when they meet in the middle, let me do a little bit of an easier one. We will get our path. Okay, oh, but wait a minute, it went for a bit longer. Why was that? We'll see that when I get into the slides. So, all right, so that's it for the demo. It is so similar to assignment 1, and the good thing is that now you're used to this framework, and if you weren't sick of grids already, I promise you'll be sick of grids by the end of this assignment. Okay, so let's get into the PowerPoint presentation, and I will explain everything there is to know about this assignment. Oh, one more thing in the demo. The other thing that we have in this assignment, I have to select the solution, is, and I apologize to Mac users, I brought a mouse specifically for this. If you hold down the right mouse button, I have this thing called connected sectors. And so a connected sector is a group of states that are all connected to each other. Connectedness meaning that there is a path possible between all of the states that are in pink. So here, I can pathfind from any of these pink ones to any of the other pink ones. But any of the ones that are not possible to be reached are not highlighted. So here, for example, here, 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 etc. Now what you'll notice is, when I select a different object size, you'll see that there's a little bit left off of those edges. And the reason for that is because the location of the object is the top left corner, right? So I'm not drawing in every single pixel that the object fills up just the top left corner. So down here you can see this, and if I select 3 by 3, it even becomes more obvious. And so this is, these are the connected sectors, and what I've done with the student code, by default, all it does is check the color. And so you've got to change this, obviously. But here, it just highlights everything that's gray, everything that's blue, everything that's green. And so we'll get into all that and how it works. Okay, that's it. That was the last thing. I always forget that part, but it's important because that's actually more work than the A* search algorithm. Okie doke. So here we're going to be talking about assignment 2, obviously, some grid pathfinding optimizations, and at the end for 6980, we'll talk about the bidirectional search. So what's new in assignment 2? I rhymed and I didn't mean it. So the A* search algorithm is new, but it's not that new because it's kind of the same algorithm just with a different selection from the open list. We've got multiple object sizes. We've got 8 directional movement now. We've got heuristic functions, connected sectors, some pre-computing and optimization if you want to, and for 6980, bidirectional search. So this is worthy of 3 weeks of an assignment. Here is the A* graph search algorithm that you will be implementing, and you can just take that and implement it. I've just included it there for you, so when you're, you have it in this version of the slides rather than need to go back to the other version of the slides. The node class has also changed a little bit because instead of just having the state, the action, and the parent, now you are going to have the G cost and the H cost, and actually I forgot to write it here, but you'll also store the F cost. So F is just equal to G plus H. And so just note here that this is more important than it was, well, this is a new thing that you're going to be storing in the child, which is the G cost. And so the child's G cost, once you generate a next node, is equal to the parent node's G cost plus the cost of the action, right? So if it took me cost 1,000 to get to a particular state, and then I generate another, to a particular node, and then I generate another node, and that costs 100, then it'll be 1,100, right? So you take the parent and you add the cost. We are working in the same XY states as assignment 1, but now we have 8 actions instead of just 4 actions. And so as before, we had up, down, left, and right in no particular order, but now we also have up, right, up, left, down left, and down right. Okay, so those are represented by changes in both the X and the Y direction. And just keep in mind that even though this slide shows them as rectangles, these are all squares. Okay, so that may be important. And now we actually do have different action costs. So if these were squares, then what this would represent is the action cost times 100, or the distance times 100. So if up, down, left, and right are cost 1, then moving in a diagonal goes a little bit further, right? So if you know Pythagoras, if you have a right triangle with sides 1 and 1, then the length of the hypotenuse would be the square root of 2. And so if we take the square root of 2, which is 1.412 or something like that, I just multiplied it by 100 so you can get integers. So when you're seeing your costs and stuff, you're not printing ... million decimal points. So these are the action costs, and I'll explain how you get those in the assignment when we get to that. Now, legal actions in assignment 1 were pretty obvious. Don't go off the map, don't go between different colors. But they get a little bit more complicated for this assignment, and what will happen here is that you'll say, that seems needlessly complicated, Dave, but then it changes from that into, oh, okay, that makes intuitive sense, I guess, and then at the end, we'll see how it's actually easier to do it this way than the other way. So that's the thought process that you'll probably go through when I describe this. So first, because now we have different object sizes, an object can only occupy a given space if all the tiles underneath are the same color, right? So if we have a 3 by 3 object, all 9 of those cells have to be the same color. You cannot have one object overlapping tiles of different colors. Objects can only move to a space if all of the new region is the same color. So when I'm moving a 3 by 3 object, up, down, left, or right, I'm actually moving to a location with 3 new squares, right? So I have to check that all of those are the same, not just one of them is the same. An object must be entirely within the map. So this is a little bit more complicated than assignment 1 because, for example, now we can't have a 2x2 or a 3x3 object beyond, for example, the very right-hand side of the map because part of it would be overlapping with the out-of-bounds area. And most complicated, but turns out to be not that complicated when we think about it a little bit, is that a diagonal move cannot allow the object to jump over a tile of another color. And that doesn't seem obvious at first, but we'll show that, we'll illustrate that now in a second. So first, the object sizes. Here we have a 1x1 object, very simple, right? It can be anywhere. The object size, the object location rather, is going to be the top left of that object. So you may think that, oh, it's going to be in the middle. No, it's in the top left because, for example, a 2x2 object has no middle, right? And so I'm just arbitrarily choosing the top left as the location. So this 2x2 is at this location. It just happens to have some other fat here on the end that it makes it a little bigger, right? And this is an object of 3x3. And so the location of this 3x3 object is whatever in the X and 0, 1, 2 in the Y. So that's the location. The next part. The object has to be able to fit somewhere. So for example, because all of the tiles underneath this object are blue, this object can fit at this location. But the object cannot fit at that location because it would be overlapping some blue tiles and some green tiles. Okay, so that is whether or not it can fit. So the first thing you have to do is know that it can actually go somewhere, and the second thing is whether or not the action is legal. So legal actions. For a 1x1, and first what I'm going to do, let me zoom in here a little bit. Let me get, actually, I got my laser pointer. Let's see, I'll use my pen here. I've never tried this before, so let's see if I can zoom in. Oh no! Why is it not zooming? Oh, because it's in the PowerPoint presenter mode. Okay, doesn't matter. You can see that, right? It's pretty good. Okay. So first, let's look at the up, down, left, and right movements. So up, down, left, and right are the same action legality as before. So I can move up, I can move down, I can move to the right, but I can't move to the left. The reason being that it would be a different color. But now let's look at the diagonal options. So first, I can move up and to the right. I can move down and to the right, but I can't move up and to the left. And the reason for that, here's my intuition. Imagine that these were actual physical blocks of wood, and we are looking from the top down at this environment where these are blocks of wood, right? So this object, in order to go from where it is, it would have to slide up here. So we're talking about this location right here. So if the object, if you take it and physically slide it up and to the left, if that action makes any of the tiles of the object overlap with a different color, then it's not a legal action. So that is why moving up left here is not a legal action, because it would slide over or jump over an object of another color. And similarly, going down and to the left would do the same thing. Okay, it would be jumping over this this cell of a different color. Now let's look at legal actions for 2x2. So it can move to the left and it can move down. It can't move up because then this tile would be overlapping this tile, right? And it has to be all the same color. Even though the destination tile of the location is still blue, there are parts of it that are not blue. And so it's not able to go up, and it's not able to go to the right for the same reason, okay? Because moving to the right, then this tile, which is now blue, would become green, and so it's not allowed to overlap. The diagonals, it can move down and to the left, but let's look at what happens when I try and take this and move it up and to the left. If I try and take it and move it up and to the left, then it will be sliding over part of this green one. And so since that's jumping over another color, then that is not a legal action. And similarly, with going down and to the right, it would be jumping over this one, and obviously it can't go up and to the right. Okay? So you see how that works? If any part of it would, as it's sliding diagonally, would touch another location, then it's not legal. And now you're saying, Dave, this seems needlessly complicated. How are we going to program that? How am I going to see if I'm sliding over another thing? It turns out that this has a really nice property that we'll get to in a little bit. So the effect that this has is pretty dramatic on the paths, because you might look at this and intuitively say, oh, I could just go diagonally up here and get from the start to the goal. But the problem is that this would be sliding over these tiles of another color. And so for here, there is no path that's legal to go up and to the right like this. We would actually have to go all the way around to the left, up and over. So there is a path, but it's not the path that seems most obvious at first. But let's trim off some of this right here. So now, let's say we're in this situation. So now, I still can't make these diagonal moves. Why? Because this tile, if I move diagonally up to the right, would be sliding over this tile, right? So the diagonal moves here aren't legal, but there is a path where I can go up, right, up, right, up, right, up. So now we can get through here, but we can't just slide diagonally. We actually have to go in sort of a staircase fashion. All right, so that's just an interesting case. Now, here's a really interesting fact about this, and it makes this so much easier than you may think it's going to be. Here's the legality for diagonal actions for a one-by-one object placed right here. I can go up and to the right. I can go down and to the right. I cannot go down and to the left because I'd be sliding over, and I can't go up and to the left because I'd be sliding over, plus it's a different color. But let's overlay the cardinal directions now, okay? So if you think you can notice the relationship between cardinal legality and diagonal legality, just put your hand up and see. Okay, right there in the front. Yep.
If it's on any of the cardinal directions, you can't go, like if it's on the left, you can't go up left or down left.
If what's on the left, sorry.
Up all, like you can't move left. You also can't move up left or down left.
Perfect. Okay, so it's kind of a hard thing to get out in words, but what we can see here is that upright is legal because going up then right, as well as right then up, is legal, right? So if I look down here, all you have to do really to know if a particular location, so this one, for example, am I allowed to go down left? Well, in order for that to be legal, I would have to be able to go down then left, as well as left and then down. And so because one of the two cardinal directions on either side of this diagonal are false, which is what you were saying, this is not a legal action. And so this is a little shortcut that helps us to prevent all those nasty calculations that we would have had to do from tiles sliding over each other, etc. So here, for example, down left isn't legal because left and then down is not legal. Here, for example, moving up right is not legal because right and then up is not legal. Okay? So what we can do then, whenever we go to see whether or not a particular diagonal action is legal, we can actually say, okay, are both the cardinal actions legal? And if both of those are legal, then the diagonal action is legal. So it's really cool. By imposing this this restriction that you can't jump over things, we have now made it so that any path that is possible via diagonal actions must also be possible via cardinal actions. Okay? So our path is possibleness is the same for both cardinal actions and for diagonal actions. So later on, when we go to talk about connectivity, we can just compute it with cardinal actions, and we don't need to worry about diagonal actions. So all of this will come together at the end for some crazy cool optimizations. All right, now let's talk about paths. At first, if I hadn't told you all of this stuff, you might think that the shortest path between this start and this goal was this path. But this is not a legal path anymore. Why? Because this is jumping over these two tiles right here. And so the shortest path would actually be be this. So you kind of have to touch the corners with the corners in order to make some of these shortest paths. The path cost is now the sum of all the action costs in the path. So for example, because these are cardinal, it's 100, 200, 300, 400, 500, 600, and now we have a diagonal action. So 600 plus 141, 741, 841, 941. And so that's how you calculate the total path cost. It's just the sum of all the action costs in the path. And so just you might think, okay, well, I guess as I'm forming the path backwards, instead of now just adding the actions to the path, then I have to sum up all the action costs. But that's not true, because your nodes now have a g cost. And so the g cost of the first node in the path is 0. Then when we do this action, we'll say that the g cost of this node is 100, because it was 0 plus 100, and so on and so forth. So when I get to this one, the g cost is 600. Then I add 141. And when I get to the node that contains the goal, its g cost is already the sum of the action costs. So I know immediately what the length of the path was just by taking the g cost of the node. Now we'll talk about the heuristic functions. And so the heuristic function, as we talk about this h of n, is the guess at how much distance that we have remaining. And so in assignment 2, I will have a function that is called estimate cost. That'll be in the search student class. It'll take in an x and a y. That's the state that we are currently at in this node of the search, as well as the goal x and the goal y. And what you'll do is you will implement 4 different heuristics. In fact, you'll just implement 3 of them, because the 0 heuristic is just 0, so you don't really need to implement that. So the first one you have to implement, and there'll be a configuration option. It's like this.config.heuristic or whatever it's called. I'll get into that. But if that's equal to dist, then you will compute the Euclidean 2D distance. So that's just Pythagorean formula. So you all know the distance formula. Otherwise, it is card, in which you will compute the 4-directional Manhattan distance. Otherwise, it is diag, in which you will compute the diagonal Manhattan distance. And that one may be the trickiest, but they're all actually pretty easy. So here you have our xy and our goal x and goal y. So the Euclidean distance, that's just the distance formula. So it's square root of the sum of the squares, or the sum of the differences of the squares. Squares of the differences, you know what I'm talking about. Here, this is the Manhattan distance. This is a very easy thing to compute. You just take the absolute value of the differences in the x's and the y's, and then you add them, right? So I have to go 1, 2, 3, 4 down, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over. So what's that? 4 plus 11? 15, right? Times 100, of course, because we're working in hundreds here. So the Manhattan distance, the 4-directional Manhattan distance, or the cardinal Manhattan distance heuristic here would be 15 times 100. The slightly trickier one is the diagonal Manhattan distance, okay? Where now you're combining cardinal movements and diagonal movements. But this formula is actually really, really simple. What you do is, you take the difference in the y and the difference in the x. Whichever one is the least, you multiply that by 141, because that's how many diagonal movements you will take. So here, for example, we have 1, 2, 3, 4, right? So I know I'm going to have, well, I have 4 versus 11. 4 is the least. So I know I have 4 diagonal movements. Okay, so 1, 2, 3, 4 diagonal movements, 4 times 141, plus the remainder in cardinal movements. That's it. So it's actually pretty easy to compute. There's just one extra step. And then the 0 heuristic, it's always just 0, right? In fact, I've already done that. Right now, by default, all of them just return 0. So you only need to edit those other 3. Take a sip. Now, the meat of this assignment, the connected states. The connected states are interesting. States are considered connected for an object of a given size if a legal path exists between them, no matter how long that path is, right? So all I care about is that it's possible to get from any of those pink states to any of the other pink states. A connected sector, now this is a term that I have coined. I don't think it's, in the textbook. A connected sector, or a connected set, or whatever you want to call it, is the entire set of states that are all connected to each other. So in assignment 2, holding the right mouse button highlights all states connected to the clicked state. And a cool thing is that connectivity is transitive, right? So if A is connected to B and B is connected to C, then you know that A is also connected to C, right? So if you have, let's say for example, you start with one set or one element in this, one location or one state in this set of connected states, and then you find one other thing that's connected to it. If you find any other thing that's connected to the first one, you know it also has to be connected to the second one. Because in the worst case, you could go from this one back to the first one, and then from the first one to the second one. So connectivity is transitive. So let's have a look here. What is connected? These two are connected, right? Because a path exists between them. These, A, B, and C, are all connected for size 1 objects. The reason they are connected for size 1 objects is because I can get from A to B, I can get from A to C, therefore I know that I can get from B to C. Now whether or not I have to go through A, that's not always necessary, and in this case it's not, because I could just come down here. Question, hand up if you can think of the answer to this. Are these connected for size 2? In the back. How come? Yeah, so essentially, for 2 by 2, these are not connected, and the tricky sort of reason that I was looking for here is that even though it looks like a 2 by 2 path is possible, you can't put something of size 2 by 2 here, right? So if it can't fit, then it's not connected. And also on the bottom, you can't put an object of size 2 by 2 there either, right? And so they're certainly not connected for 3 by 3. But these are connected for size 2. Right? Because I can, from A to C, I can go up and then over. From A to B, I could go down, then over, then up. And from B to C, well, I don't need to have a separate path. I could go from B to A to C, but in this case, I could go over and then down and then over. So these are connected for size 2, but they are not connected for size 3. And so this is the other case where, yes, I can fit an object of size 3 at A and B and C, but there's no path from C to A. There's no path from A to B, right? Because there's only an opening of size 2 here. So these are not connected for size 3. And of course, the trivial example where there are just different colors, then these are also not connected because I can't get there, so they're very sad. All right, so this would be a connected sector for size 1, meaning that anything that is currently colored pink is connected to all of the other things that are colored pink. Okay, so it is our job now to, and there will be different connected sectors here. And now you may be thinking, well, geez, why are, like, this seems really complicated, right? Now we're sort of doing like an all pairs shortest path calculation, but it turns out there's a way to do this that makes this really fast and interesting. All right, so computing connectivity. So a diagonal move is only legal if both surrounding cardinal actions is also legal. This means that a path with diagonal moves only exists, a diagonal moves only exists if another path with only cardinal moves also exists, okay? So we talked about that before. So if any path exists with any diagonals in it, it also has to exist with cardinal actions. So this means, therefore, cardinal connectivity is the same as diagonal connectivity, and it's a bit easier to compute. So let's use breadth first search. So breadth first search rears its ugly head again, and you are going to have to do it in this. But let's talk, about a special algorithm. Okay, so you might be thinking, I have to do a BFS from every possible state to every possible other state. Oh my God, this is going to take forever. But it turns out that that's not the case, and here's why. So here's the algorithm. I'm going to explain the algorithm visually, and then I'll give you the pseudocode for the algorithm. So what we're going to do is we're going to start up here in the top left. We're going to iterate over everything in the map. But we're going to start in the top left, and we're going to start from here, run this BFS. Then we're going to start from here, run the BFS. Then we're going to start from here, run the BFS. And you might think, okay, that's n squared BFSs. That's a lot of work. But the amortized time complexity will actually be very interesting. So what I'm going to do is okay, I've got everything marked as a 0 initially. That's important. So everything's a 0. I'm going to start in that top left and I'm going to mark it a 1. Okay? So I've taken my 0, I've gone up by 1, now I have a 1. Now what I'm going to do is I'm going to BFS out from that 1. And the only other condition is that in order to start a BFS, I have to be able to fit the object there, right? Because it's not connected if it can't fit there. So first I'm going to check if it fits. But I'm doing this one with object size 1. So of course it can fit. The only other condition is that in order to start a BFS, it has to be a 0. Why? Okay, we'll see in a second. So let's start with a 1. Now we're going to BFS in cardinal directions. So I go outward from here, I fill 1s in like this, then like this, then like this, until I have touched everything with that BFS. Now that BFS has marked all the things that were what was connected to this top left cell with a 1. And because connectivity is transitive, so if this one is connected to this one, and this one is connected to this one, then this one's also connected to that one. So in one BFS, I've computed the entire set of connectivity, right? So second step, I've done the BFS starting at this cell. Now I start at this cell, but it's already non-zero. If it's non-zero, it means it's already part of a connected sector. And if it's already part of a connected sector, then I've already computed its connectivity, so I can skip it. So then I keep going until I get to something. Okay, now we have a 0, right? So I do another BFS, but I increase the number. So now this is my second connected sector. So this gets a 2. Then I BFS out from there until I've completed all of those. And then my BFS is done here, and I know, okay, now anything that has a 2 is connected to anything else that has a 2, but not to any other number, right? So now I would keep going. So all these have 2s. Okay, these are non-zero, these are non-zero, these are non-zero. Okay, I have another 0. Start a BFS from here. Here's my BFS with a 3. So I increase the number, I BFS outward, and then I keep doing this, and I eventually get this grid of integers. And what this grid of integers I can do now is in constant time, instantaneously with just a lookup, I can say, is this cell connected to this cell? Well, if the numbers are different, then no. And if the numbers are the same, then yes. So I've tried to start a BFS for every single thing in this grid, but if you actually add up the number of node expansions in these BFSs, we only get something the size of the grid because we skipped everything that was already done. Right? Isn't that cool? How the amortized time complexity of this is just touching each cell in the grid once. So the only other thing is that as I'm doing this BFS, you might say, oh, but now you've got to create a closed list for each of these BFSs, and that's kind of expensive. We actually don't. Why? Because if the number is not 0, treat it as in the closed list. Right? Because we've already touched it. And so if we've already touched it, we don't. So for example, when I'm computing the children of this one, I look left, oh, I've already done that one because it's non-zero. So for these BFSs, I do not need to create a separate closed list structure because the connected sector matrix, if you will, is already acting like all of these closed lists. Yes?
Are we supposed to implement a new BFS, or can we not just use the BFS we wrote for assignment 1?
I would suggest a different one because A, you don't need a separate closed list. So the question was, can we just implement BFS from assignment 1? Yes, but it's going to be in a new function. Like you can copy and paste the code, right, and do it here. But I have a couple of other optimizations. So I should have just said save questions till the end because we'll answer that question in a bit. So you probably shouldn't be using that kind of slow version of BFS that we did in assignment 1. Okay, so those are the connected sectors. So here is the compute sectors code. So what I'm going to do is I am going to create a new, I'm just calling this a grid, but it's essentially just an array of arrays. It's a 2D array, the size of the map that has all zeros. Okay? Then my initial sector number is going to be 0. Then what I do, and this probably shouldn't be indented like this, but it doesn't matter. For each of the x's and for each of the y's, I am going to start a BFS here if it's 0 and my object can fit. So here I'm just saying if the sector number is not 0 or the object cannot fit here, then continue on to the next one, right? Otherwise, if it can fit and it's not 0, I know that I'm about to compute a new connected sector, so I increase the sector number by 1 to say that, okay, these new numbers are a new connected sector, and then I do a cardinal BFS outward, starting at xy, marking it as this sector number. So because this cardinal BFS is different enough, like you have to be marking in integers and stuff, you probably shouldn't just be reusing the same code. And then we're going to have a function, isConnected, which is x1, y1, x2, y2, that asks, are these two states connected? That's just, hey, are the sector numbers the same? That's it. Now, the only other thing that you have to do is that when you construct the object for your search student, you have to do this for all the different object sizes, right? So if I select different object sizes in my UI, it's not recalling the constructor for your thing. So here, what you would actually have in the end, and this is important, is that instead of a 2D array, it's actually a 2D array of arrays. So here, for example, instead of just storing one sector number, you would store, like, you would have x1, y1, and then s, where s is the size, right? So you would have the connected sectors for size 1, the connected sectors for size 2, and for size 3. Okay, so the connectivity check, two tiles are connected if their pre-computed sector number is the same. We can use this as a pre-check to see if a path is possible before computing it. So, if the start and the goal aren't connected, done. I can instantly know that, and I don't have to do any search, right? Now, so let's look at some bigger object sizes for this. So this is the case of 3 by 3. So for example, this location for 3 by 3 is connected to this location, but they are not connected to this location because the object can't fit there. So what I will find is that for this map, for an object of size 3 by 3, there are the connected sectors. Those are the locations where the object can fit. And the cool thing is that if I start with zeros everywhere, if I ever looked up in the connected sector map and found a 0, I know that it can't fit there. So now in my search, when I'm generating legal actions, I no longer need to do something. So for example, a 3 by 3 object, what I may have needed to do before is say, is this the same as this, and this, and this, and this, and this, and this, and this? It's 9 checks, right? But now I can just look up in the sector map and say, is it a 0? Instantly I know if it can fit or not. So all the legal action stuff and all the can fit stuff, you only use it in that initial BFS, not in the eventual search. And just keep in mind that all of this is only possible because we're working in these grids. If you have an arbitrary graph, it's much more difficult to make structures like this. But I wanted to show you, if you're talking about things like video games, for example, video games are often represented in these grid structures, and so you can make really fast pathfinding. So the same thing for an object of size 3. I'll just go through this really quick. Here's what we have in the end. So all of these are connected, all the 1s, all the 2s are connected, all the 3s are connected, but and this 4 is connected, but it's not connected to anything else. So if I want to know if something fits, I just check to see if it's a 0 or not, and then I'll know if it fits. So your search student object will not, I should have just waited. I forgot that I had a slide on this. It will not reconstruct if a different object size is selected, so you must compute connectivity of all sizes in compute sectors when your object constructs. So instead of having just this dot sectors xy, you just have another dimension on there. So each of those is actually a little array, and so this is the sector xy at size s. So you can use a 3D array or a 2D array of arrays, however you think about it, right, in your head that makes it easier is fine. In practice, what I do, because sizes, there's no size 0, right? So it's size 1, 2, or 3. So I actually make this array 1 larger so that I can index it by the size, right? So size 0 doesn't really mean anything, so we could ignore those values. But this is index 1 is size 1, index 2 is size 2, index 3 is size 3. So that's what I do in my solution code. Okay, I got to speed up a bit. Oh, on the speed optimizations. So the following optimizations will not affect the number of nodes generated, but will dramatically speed up the running time. None of these optimizations are required for getting full marks, but some of them may be required if you want to actually make it look fast and perform smoothly on your laptop or whatever. So here's the compute sector optimization. I think I just said this. For large object sizes, we may have some tiles that have a 0 value. That means the object can't fit. So by pre-computing these values, we can use them later instead of doing the full object size check to see if all the underlying tiles have the same value. I just said that. I don't need to repeat that. Legal action optimization. The rule of no jumping over diagonal actually gives us an interesting property. A diagonal move of xy is only legal if both xy and yx are also legal. This property holds for all object sizes. So this is here. We just talked about that. I don't need to say that again. So, yeah, so that's an optimization you can use if you want. The most commonly called function in A2 is probably isLegalAction, since it's called whenever a child node is generated. We can use the pre-computed connectivity sectors to check for legal cardinal actions, since actions are only legal if the source and destination tiles are connected, right? So we've already done connectivity checking, and if 2 adjacent tiles are connected, it means an action is legal. Cool. So let's have a look at this. Action for computing A, B, right? So A and B, if they're connected, then the action to go from A to B is legal. So we no longer have this huge isLegalAction function. We would only do that. Please, I gotta wait till the end. I'm following behind here. Hopefully it will be answered for you. For diagonal actions, look at AD. AD is only legal if AB, AC, and CD and BD are also legal, right? We just talked about that. AB is legal if A and B are connected. AB, BD, AC, and CD are legal if each of A, B, C, and D are all connected. So if A, B, C, D are all connected, then AD is legal. Okay? So if you check all 4 of those to see if they're connected, then I know the diagonal action is legal. And since connectivity is transitive, if AB and BD are connected, then A and D are connected. And so that means that if AB, AC, and AD are connected, so that's 3 checks, then the action is legal. So now, when I'm actually doing my A star search, my isLegalAction function is just 3 Boolean checks. Are these 2 connected? Are those 2 connected? And are those 2 connected? And so that's it. That's all I have to do in my isLegalAction. Here's another one, legal action optimization. Our environment is static. It never changes. Tiles will have the same legal actions for a given object size every time you visit them. So you could just pre-compute all the legal actions for all the tiles and just iterate over that list of legal actions every time you do a search. This will result in a lot of time saved. So you could do something like this, where you make another array the size of the environment, and each cell of that holds a list of all the actions that are legal. So now, instead of iterating over all 8 possible actions to check if they're legal, you can just iterate over the actions that you know are legal, right? So this saves a lot of time as well. Here is a closed list optimization. I've kind of hinted at this already in the hash table lecture, but the closed list stores unique states. each state on the map will either be in the closed list or not in the closed list. So store a 2D array of true and falses, the same size as the map, to denote whether or not it's in the closed list. And so closed list membership is now constant time, rather than having to look up the entire closed list. I don't know why that slide is there, so I'll skip it. Sorry about that. Open list optimization. You can, if you want to, just use a standard array for the open list and put nodes in it. And then every time you want to select a min f, you would have to iterate over the entire open list and find the one with the minimum f value. Or, as I'll show you in a bit, I have included a binary heap data structure, which will be much faster. So if you use that, what I recommend doing is implementing it with the open list as an array first. Yes, it will be a little bit slower, but then you'll know whether or not your algorithm works. The worst thing you can do is use some new data structure that you've never used before, write your whole algorithm, and now if you're not getting the correct path, you're not sure if your algorithm is broken or if the binary heap, you're not using it correctly, right? So I recommend doing everything naively first until your algorithm works, and then later do this. So with the new binary heap, you pass it in a function to be sorted upon a node. So you can just say return node.f. I'll leave that to you to figure out. It's not very difficult. So the open list for the binary heap, if you push a node, it adds the node and keeps it sorted. If you pop a node, it will return the node with the minimum value of the sorting function that you put in. So that will remove it from the list. But it also has a function called peek, which looks at it. It gives you the minimum node, but it doesn't remove it. So this is for the 6980 folks, where you have to look at both open lists to compare them, but you don't want to remove from both open lists. So you're going to want to look at the minimum f from both open lists and then just take it out of the one that had the minimum one. Okay? Here is BFS performance notes. Actually, implementing BFS with a queue that we've talked about results in reduced performance. So if you're actually using an array with shift, that's a terribly slow operation. Vector-based implemented queue needs to left shift all elements to pop from the front, which is very slow in practice. So performing a lookup in a closed list can also be slow if implemented poorly. I'm probably going to go like 5 minutes late on this lecture. If I do, feel free to leave, but I'll just get it all for the recording. So here is how to avoid using a queue and actually removing things from that list. So we're going to simulate a queue just using a vector. To insert into the queue, I'm going to describe it first and then show you. So if you don't get it from the text, I'll show you an example. To insert into the queue, push the state into the back of the vector as normal. Instead of removing from the front of the queue, simply advance an index pointer. So it's like you're throwing it out, but you're not throwing it out. So instead of checking if the queue is empty, you check to see if the pointer is now pointing at the end. Okay, what the hell does that mean? Here's an example. I'm going to implement BFS with an array or a vector that does not actually remove anything. So I'm going to put my root node in there. So when it's the root node, I've only got one thing in there. So now I'm going to take that out and add it to the closed list. But instead of actually taking it out, I add the new things in, and then I have some sort of pointer or index saying the actual front of my queue is now that thing. Okay? So now when I take this one out and add some more things, here's what happens. I've added a bunch, and then I take my index and I point it to the next thing. Right? So these things, I'm no longer having to remove all these things and shift all the contents over to the left. Array.shift is a linear time operation. This is a constant time operation. So then if I keep popping stuff from the list, now I can check, okay, does the end pointer actually match the beginning pointer? Now I know that it's empty. You don't have to do that, but it will be faster if you do that, okay? So this is another technique where we can trade memory for speed. And also why I don't recommend using the BFS that you did for assignment 1 for this one, because this one will be much faster. Next, tie-breaking F values. Many nodes in the open list contain identical values for F equal G plus H. How you tie break those can affect how your path looks and the running time of your algorithm. It can also affect the number of node expansions. So if I just take a random f value, then my path can look like this. It'll still be optimal, but it's however that binary heap added stuff to it, it's kind of random. I'm essentially taking a random node with the minimum f value. But it turns out that if you tie break with min g, you'll be expanding all the nodes in this parallelogram, right? Because you're always taking the thing that's the closest. So it turns out all of these red nodes all have the exact same value for f, right? Because there's no obstacles. So you could have an A star where you go from the top left to the bottom right and you expand every single node in the environment almost. But instead of tie breaking by G, you tie break on H, you go straight to the goal if there's no obstacles. Okay? So I would recommend tie breaking based on H if you can, because you'll go from expanding that many nodes to expanding that many nodes and get the exact same result. And wouldn't you want to have that? Okay, 6980, bidirectional search. So far, we've looked at only finding a path from the start to the goal. What about the other way around? What if we went from the goal to the start? Or what if we did both? Bidirectional search goes from the start to the goal and from the goal to the start. The search stops when the graphs intersect, so when your closed lists intersect. So intuitively, we can visualize why bidirectional search may save computation. Search algorithms work out from the start, creating a radius of expansion. So which has a larger total area? One circle with diameter d, or two circles with diameter d over 2. Okay? So if we look, here's one example of bidirectional search. Here's the start, here's the goal. If we had this instead, this circle is what unidirectional search would expand, versus ideally, these two circles is what bidirectional search would expand. Okay? So the area of the circle is the expansion, so the sum of the small circle areas are less than the big one. In practice, it's kind of hard to get this performance, but bidirectional search can expand fewer nodes than unidirectional search. You may have to make search moderations. So how do you implement bidirectional search? I'm leaving this a bit fuzzy to the grad students because I want you to do a little bit of independent thought. So you may use two open or closed lists. You add the start node to its open list, you add the goal node to its closed list. And just remember, it's a little bit tricky because the heuristic is backwards for the second closed list. Because anything, the second open list. Because anything from that, you're now estimating the distance to the start rather than to the goal, right? So could you just use one of each list? I don't know. Add a start and a goal node to both to the open, choose the minimum f from the single open. Be careful of the heuristic function in this case. So if you can get it to work with a single open list, you can do that as well. I think my solution code used two open lists. So there's a new goal test condition. How do I know when I've reached the goal? Is it when the closed lists intersect? Is it when the open lists intersect? Try them both out. See what you get. Node expansion options. Do you just take the minimum f from one of them? From both of them? Do you expand the minimum from all of them? You could have some bounding strategies in there. There's lots of cool things that you can do with bidirectional search. But here is the kicker. Optimality. Can we ensure optimality with bidirectional search? Well, look at this. There's a purple node right here. Two shortest paths to a common state may not be the overall shortest path between the two states. So here we have a start and a goal, and we've done some bidirectional search. And so this purple node is the first node that's in both closed lists. And so what that means is this is the optimal path from the goal to the purple node, and this is the optimal path from the start to the purple node. But if I just take these two paths and add them together, that is not the optimal path from the start to the goal. That would be going through here, just taking this diagonal, right? So it missed the optimal one. So if we stop at the first solution, it may not be the optimal one. So for A star, we can be optimal. So what we do is we set an initial solution cost to infinity. So I haven't found a path yet, so my path cost is infinity, okay? Whenever you find a new, better solution, set that path cost to the cost that you found. So I would set initially, okay, I found this path, I'm going to set my best path so far to that one. Now, I'm going to stop when the next node's F cost is greater than the best solution so far. Why? Because A star guarantees me I'm searching everything with an F cost less than the optimal path, right? So if the node's F cost that I pull from either open list is greater than any path cost that I've found so far, I know that I must have found the optimal solution because I've searched everything up to a path that's worse than this one, okay? So in practice, this doesn't save time, but it is optimal. So for A2 requirements for 6980, what I'm recommending is the following. Use two open and closed lists, add the start to the start list, the goal to the goal closed list. Return the contents of both open and closed lists for the visualization, so I can see them both growing. So in the get open and get closed, you just have to add both of them. Animated search should show nodes being selected from both of the lists. The path should be formed when both lists meet. It should show a path if one is possible. Optimal paths and tests are not necessary for most of the marks, but I meant to change this to 5%. So the last 5% is from your bidirectional search actually returning optimal paths. Okay, so you'll get 95 if you get bidirectional search working. You'll get 100 if it has the optimal paths. If you are a grad student, you might be interested in this sort of thing. So Nathan Sturdivant and Ariel Fellner, they're both colleagues of mine. They are the world experts on bidirectional search. This paper has some very interesting properties of bidirectional search. I will not be putting this on the tests or on the exams. It's just, hey, if you're interested, here's a bunch of theory about bidirectional search that I'm not going to go into. Here's another website that has a really cool bidirectional search demo that you can look at if you want to.
So you just watched 2025 Dave give the first part of this lecture, and now 2026 Dave is going to give the second part. The reason I cut out the old part and put this part in is because some of the code has changed, and also I was kind of rushed in that class. I only had about 10 minutes to present all the code, and I wanted to go into a little bit more detail than I could the last time. So here we have assignment number 2. And just like last time, I'll go through all the files and then I'll go through the skeleton code. So over here we can see that the marks file has been split into 2 files now rather than putting everything into just a single file. That makes it a bit easier for the marker. Next we have A2 GUI. You can ignore that file. Next we have a binary heap.js, and this is a binary heap class that I found outside and online, and you can use this as a priority queue for your open list if you want to. However, I'll get into this in a bit more detail later. You don't really need to know how the binary heap works exactly. However, just know that you can push things into it and you can pop things out of it. And based on the sorting function that you passed into the constructor of the binary heap, the pop function will return the minimum element. So you'll always have that constant time access to the minimum element. However, please implement the entire assignment using just a basic array and get all that to work to make sure all of your code works before you mess around with the binary heap. And that should be pretty easy to do because you can just make changes to your open list class without making any changes to the rest of your code. Next, we have the environment.js, and this is very similar to assignment 1. However, the one major difference is now because our objects have different sizes, the isOutOfBounds function now has an extra parameter, which is called size. And so if it's size 1, you'll pass a 1 in here, size 2, a 2, etc. And so this is because if you have an object that's like over on the left-hand side of the screen, or on the right-hand side of the screen, you need to take the size into account. So if I'm only 2 elements from the right-hand side of the screen, then an object of size 3 won't actually fit on that part of the screen, and similar with the bottom of the screen. So that's it for the UI. The rest of the environment. The rest is the same. Next is GUI. You can ignore all of that. That's the same as A1. Index.html, that's the same as well. And obviously, I'm going to skip over the solution files. So again, most of the work is going to be done inside this search student class. And you're very familiar with this now because hopefully you've finished assignment 1 by the time you're looking at this. So what I'm going to do is up at the top here, because there's a lot to do in this assignment, I've done this sort of recommended order of completing things. And what this is, it's the same thing as I mentioned in a previous lecture about, you know, if we're building a house here, we have to build the floor and then test the floor and then build the walls and then test the walls out and etc. So we can't put the roof on the house first. And what I noticed about assignment 1 is a bunch of you were trying to put the roof on the house first and sort of writing 300 lines of code and then saying, I don't know where the errors are. So hopefully this will help you out with assignment 2 and tell you exactly what order that I think you should implement things in. So very first thing here, step number 0, is to implement the open and close lists in their basic form. What I mean by basic form here is just the simplest possible form that you know works so that you can get the algorithm running and the tests passing without having to worrying about any optimizations or anything like that. So here we have the open list, and the open list class is going to be almost identical to the open list from the last one, except the get first and get last functions are going to be replaced by this get minf function. So in the last assignment 1, if I go over here to search student, I had get first and get last, and that's because we were using these to simulate a queue and a stack for BFS and DFS, but we're no longer doing that for assignment 2. We just have one version of the open list that's going to be getting the minimum F value because we're doing the A* search algorithm. And so the rest is the same, so get states, size, add, all of that's the same, except we have this get minf. And like I was saying before, I recommend just implementing the open list as like a basic array that you're adding nodes to at first. And then this function would just search through that array for the minimum value and then remove it and return that from the function. So I recommend doing that at first before trying that binary heap. Next, we have the close list, and the close list can actually literally be identical to the first assignment. So again, the close list is just storing states, and there's no difference between that with the A* search algorithm and how it was before. So you just have your add, contains, and get states functions, and you're completely allowed to just copy and paste the code that you wrote from assignment 1. So whatever you had from assignment 1, you can paste it here, and it should work. Of course, you're allowed to change it and put in some optimizations. Just make sure not to change the names of any of the classes or anything like that. So that's the open and the close list. And before I go to the next part up here, I'm going to first look at the constructor of the search student class because there's nothing in that list that specifically mentions this, but I did want to go through all the parameters for you. So first, like assignment 1, we have the this.config, and that's what gets set up by the user interface. So as you change things in the user interface, that's modifying this.config. And so there are a few different things in this one than we had before. Oh, look, I found a little error, so I'm going to remove that. Search.strategy is no longer a thing. So we're not doing BFS and DFS in assignment 2. However, what we are going to be doing is now we're going to have config.actions. So you had config.actions in the first assignment. However, what I saw was that some people were sort of implementing their own actions array. But please be sure to use config.actions in this one because this is set up by the user interface to either be 4 actions or 8 actions. So let's just have a look at what that means in the user interface itself. So if I come over here, there's of course this legal actions part. And if that's set to 8 directions, or if that's set to 4 directions, then that will modify config.actions. So be sure that you're using that and not to hard code your own actions array, because that will just not work in this assignment. You need to know which actions are going to be legal for your search. Next is config.action costs I. And so what this means is that, for example, if I'm using this.config.actions 2, for example, so let's say that's just the move up action, then this.config.action costs 2, that's going to be the cost of this action. And remember that this could either be of length 4 or of length 7. Now, the reason you didn't really have to use this one in assignment 1 was because all the action costs were the same. They were all just cost 100. But you have to use this one now in assignment 2 because there could be some difference in the action costs. So up, down, left, and right are going to be 100, and all of the diagonal actions are going to be 141. For the 6980 folks in the class, you do have to look out for this one. So this is config.bidirectional. So because we're doing bidirectional search, this config.bidirectional is saying whether or not we're actually doing bidirectional search. And just like last time when we did IDDFS, if we scroll down here to the search iteration function, here, one of the first things that we do is we say, okay, if this is bidirectional search, then do the bidirectional search function instead. And so that's just like the IDDFS thing last time. However, last time we had a string and now we just have this Boolean. All of these variables are the same as assignment 1, except now we have this.size. And so this.size is the size of the object that's currently selected in the user interface. By default, that's going to be 1, but it can be changed. So if I come over here and I set the object size, that can either be 1 by 1, 2 by 2, or 3 by 3. So over here, if this is set to 1, that means 1 by 1, 2 means 2 by 2, 3 means 3 by 3. And the cost is just the cost of the solution that we found if we find one. I'll come back to this one a little later. Actually, let me just do it now. So if you end up using the binary heap object here for your open list, one of the things here for the constructor is the score function. And so the score function, what this does is essentially a priority queue, and you want to get the minimum thing. And so it needs to know how you actually want to sort the nodes. And so in here, this is just an option, or this is an example of a sorting function, which takes in a node and returns the f value. Okay, so what this will do is down here, if we look at the node class, there's a bunch of different things in a node, right? And so the binary heap is essentially, you need to tell it, hey, sort this by this.f, which is what that function is doing. And so here, what you could actually do with this, what I would recommend, is if you end up using the binary heaps, and then you can actually remove this from the constructor, and you can put this up here in the open list. So if I do that, let me just show you what that looks like. And so here I can just have sort function, which takes in a node and returns node.f. And then in the constructor where I set up my binary heap, I can just pass in this.sort function as the function. Or if you don't want to do it that way, you could also just define the function as we did in the previous constructor up here. So that's up to you. I'm just going to leave it for now back where it was down here just as some example code. But as of right now, nothing actually uses this, and so you can remove it if you want to. Next, we have some similar variables to assignment 1, so all of these are the same. And down here, I call this.compute sectors, which we'll get to in a little bit. I don't want to get ahead of ourselves, but just to mention that the sector computation is going to be done within the constructor. So whenever you construct a new search, so for example, when you come up here and you select solution or you select student, that is actually what's constructing the object for your search, and that's what's calling the compute sectors function. So that's when that's called. Okay, so that was implement the open and close list and the constructor. Next, so the first real thing that we're going to have to do to the class is to construct the function which computes whether a given size agent can fit in a given XY location. And this is going to be used by several different functions, including compute sectors and isLegalAction. So that's the canFit function. And so here's the canFit function. It's going to take in an X and a Y location on the map, and it's going to take in a size. And so what you have to do, if you go back to the notes section of the video, is essentially say, okay, let's just zoom in here. Oh, let me select a 3x3 square. So for example, this 3x3 square can fit anywhere here in the blue, But if we move it down so that it's overlapping with 2 or more different colors, then it can't fit there. So what you have to do is you have to use that this.size variable and loop from xy up to the size, so x plus size, y plus size, and check all for, so for example, for 2 by 2, that would be 4 different locations, and for 3 by 3, that would be 9 different locations. And so in the code here, you would write that loop right here, and essentially you're just saying, okay, if any of the other squares other than xy are different than xy, then return false. Otherwise, you just return true. And so that's what the can function, the can fit function is. Next, complete the compute sectors algorithm using the 4-directional BFS as shown in the class slides. So the compute sectors function is going to be down here. And so this is this function. It doesn't return anything. You're just essentially going to set up this dot sectors. That's that array that I talked about. So it's the grid where you're going to store all the sector numbers. And you can do this, you just iterate over and you set up, okay, this is a blank array initially, but now I'm going to set up a 2D array of size x by y. And then inside it, I'm going to have the sector numbers for all the different things, for all the different sizes. So for example, at the end, what you're probably going to have when it's all working is a 3D array. So that's an array of arrays. The way I sort of get this, I think about this in my head, it's a bit easier than a 3-dimensional array, is just say, this is a 2-dimensional array of arrays. And so I'm going to have 3 different sizes, and I'm going to have width, different x's, and height, different y's. So that's where this function goes, and that's what you'll have. Now, obviously, this is not valid JavaScript, but what you'll want to be able to do in another function is say this.sectors, x, y, size, or let's just give examples like 2, 3, 1. So this would be the sector number of x equal to 2, y equal to 3, and the size equal to 1. And then you can check to see if that is equal to, for example, let's say we moved 1 to the right, and so this would be a 3. And so that's saying, hey, are these two places connected in our environment? And that's how you would call that later. So let me just set this back. And we'll go up to the next thing. This is probably going to be one of the trickier parts because, as I said a bunch of times previously, the actual A-star search is going to be really trivial because you've already written that algorithm from assignment 1. You just need to change how the node comes off of the open list. So the code for your search iteration is actually going to be quite similar, at least for the 3,200 people. So a lot of your effort is going to be spent here inside compute sectors. Next, use the results of step 2 to complete the isConnected function and test it with the user interface. So what does that mean? So if we come down here to isConnected, I think I talked about this in the demo video, but essentially this function is going to return whether or not location x, x1, y1 is connected to x2, y2 for an object of a given size. And so if I come back out here, and I did show this in the demo, if I just take 1 by 1 square for the student A-star and I right click, you see how everything of the same color, even though it's not connected, everything of the same color is being highlighted? That's because in the demo code here, I'm just saying, hey, is this.grid.get x1, y1, is that equal to this.grid.get x2, y2? So that's literally just asking, are they the same color? But it's not saying, are they actually connected, right? Because this section here obviously isn't connected to this one over here. So if this is working properly for you, then you should see something like this. So I just selected the solution. So all of these are connected, all of these are connected, etc. And again, if you select an object of size 3 by 3, then the connected sectors are going to change. Okay? So that's what this function does. And this function is really, really easy. All you're doing is you're doing what I did up here, where I said this.sectors x1, y1 size, is that equal to this.sectors x2, y2 size? And so this should just be a little one-liner here that does that. So all the work there is really in the computing of the sectors, not the checking of the sectors. All right, next we're going to look at the isLegalAction function. And the isLegalAction function is going to be used by search iteration in order to check your legal actions. So this is going to be, in theory, the same thing as assignment 1. So there are things that you need to check, but I did talk about some optimizations from the slides, right? So if we looked back at assignment 1 and we look at search student, so again, this is assignment 1. I said these are the 3 things that you need to do. So you do need to do those as well for assignment 2. However, if you go back to the slides, I did mention some other things that you need to do that accounts for the size. Okay, and just remember that size is not actually a parameter into this function. So you'll use this .size to tell whether or not it's a legal action for a given size. And so the this .size, that will be set when I click here. And so isLegalAction does not need to take in the size that's already here. And you can use the connected sector optimization that I talked about in the slides to do this if you want your code to be really fast. Or you could literally go through and use canFit and a bunch of loops and stuff to do that if you want to as well. Next, we have the start search function. This is going to be pretty identical to assignment 1. So here's the start search function. So again, I've done a bunch of things for you, but you're going to have to come in here and edit it to like create the new open and close list, create the root node and add it, etc. Any other things that you're doing. But that's very similar to assignment 1, so I don't need to talk about that too much. Then there's the get open and get closed functions. So this is identical to assignment 1. This is get open and get closed. And again, just like assignment 1, what I recommend is that you call these functions for the open and close lists, because the open and close lists know how they're storing things. And that's how you would do that is... So the reason you want to do that as one of the first things that you do is so that when you actually go to run your code later, you can use this to debug. So it's properly drawing the open and close lists. Just one thing to note is that in the binary heap, if you do end up using the binary heap, then all the nodes are going to be stored in the this.content array. And so the this.content array, that is what you would loop over. And so if you did have, say for example, you did have this.open equals new binary heap, and then you have your sort function that you'll pass in that I don't have defined here yet, then what you would do is this.open.content, that's going to be the array that actually stores the things that you need to iterate over in order to return the states properly for the user interface. So just keep that in mind. All right, once you have that done, then you're going to move on to the search iteration function. And that's going to be done first. What I recommend is do that with a heuristic of 0. And if it does, then it should behave just like uniform cost search, where it expands outward in a circle. So if you do that, then you come over here and you have solution A star, then that should work like this. So if I have a 0 heuristic, let me go back to a 1x1 square, then you'll know that it's working. Oops, I meant to have an animated search here. You'll know that it's working because it's going out in a circle like this. So again, A star with a heuristic of 0 is going to set the heuristic to 0, and so therefore it's choosing the minimum G value, which is the one that's closest to the center, or to the start, sorry. So that's why it's behaving like uniform cost search. So the reason that I want you to not do the heuristics first is because if you run A star with an inconsistent heuristic, then it won't be correct and you won't pass the tests. And so what this does is, because we're certain that the heuristic of 0 is always a consistent heuristic, then what this does is it allows you to be certain that your algorithm is correct before you start doing the different heuristic functions. Because if you did the heuristic functions first, and then you test your algorithm and you don't get the correct solutions, then you're not really sure if there's an error in your algorithm or there's an error in your heuristic function. And so that's why I recommend doing search iteration first. So if I come down here to search iteration, I have the same example code that I gave for last time. So you can just literally delete that if you want to. Well, actually do delete that because it's not going to be correct if you don't delete it. Next, I have this example here. So a lot of people had this question for assignment 1, which is during my while my animated search is happening, I'm not seeing those gray nodes. So if I come over here and do the solution while it's animating, you should see this this gray line. And a lot of people weren't seeing that. And the reason they weren't seeing it is because that gray, those gray lines are being drawn with respect to the this.node. So whenever you go to select your node, you'll just say this.node equals this.open.getMinF, because that's the function that we created in the open list. Next, I have some sample code here for properly iterating over the actions. And so here I just said, okay, my index is going to be this a variable. A goes to this.config.actions.length, a++. So here we have the action, that's this.config.actions a, and the cost is going to be this.cost.actionCosts a. I'll just delete this now. I was just testing something earlier. And so this is how we loop over the actions. And then in here, you can call, if this is a legal action, then form the child nodes, etc. So that's how you do that. And just keep in mind that in the assignment 1, you didn't really have to care about the G cost. So if I do have a node, so if I let me just do this so I don't run into these syntax errors in VS Code. So this.node has a G cost, and I didn't really have to worry about that in assignment 1 because all of our action costs were 100. So what we could do in assignment 1 is just say, hey, the cost of the path is just equal to the number of actions in the path, which is the length of the path times 100. But this time we actually do have to worry about it because if we have if we have a child, right? So we have a child node and we set that up to be something. Here we're going to say that the child node .g, that's going to be equal to the node, which is the parent's G cost, plus the action cost that we just got here. And so we do need to keep track of the G costs because different actions can have different costs. And then at the end, when we find our solution, then the node which contains the goal state, its G cost is going to be the solution cost. And so you can just set this.cost equal to that. And so I just set up that sample loop for you there. And just so the student one doesn't infinitely loop, you have to set this.inProgress properly. Okay, so the next one is next you're going to implement the estimate cost functions, and you're going to use that with a star. So here we are going to say estimate cost. Okay, so this is the function where you pass in an x and a y, and a gx and a gy, and this is returning one of 4 different heuristic values, and these are just the guesses at how far we have left to go. So those 4 functions are the 0 heuristic, which is already implemented for you, so you don't have to change that. It literally just returns 0. We have the diagonal Manhattan distance that was covered in the slides. We have the cardinal Manhattan distance. Cardinal just means 4 directions, so up, down, left, and right. And then the last one is the 2D Euclidean distance. So this is just the distance formula, Pythagoras. That's what you would implement from that. And this.config.heuristic, again, that is going to be automatically changed for you when you come in here in the UI and you select it. Okay? So the different heuristic is going to be selected and put into this.config when you do that. Okay. I didn't include that up here. So config.heuristic, heuristic function used. So I'll just put that, I'll put that up here. So make sure when you're creating that new node in your search iteration function down here, that you are the h value that you're creating. So the node class down here takes in an x, a y, an action, and a parent. Now that's the same from assignment 1. However, it's also going to take in the G. Whenever you create a child node, that's going to be the G cost of the parent plus the cost of the action. And then you also pass in the H value. So that H value is where you call this.estimate cost, which I have lost here. Yeah, so that is going to be the H value. And then the node itself is going to set up the F value, which is just G plus H. And so that's where you're going to actually call that function once you've created it. Make sure that you test this function before you run your algorithm. So just call this function somewhere, maybe print out, you can hard code this. So for example, in your start search function, one of the ways that I debugged this, if I can get to start search, is here you can just hard code something. Like you can say console.log this.estimate cost. And then you can put in something here, like from 0, 0 to 10, 10, right? And so if this is the diagonal heuristic, then this is going to be what? It's going to be 10 action, 10 diagonals, so that's like 1410, I believe. If it's not, then it's going to be 20. If it's cardinal, it's going to be 20 or 2000, I guess, because you'll have to go all the way over and all the way down. And if this is the distance, then this will just be 10 times the square root of 2, whatever that is, times 100. And so that's how I would test that to make sure your functions work before you actually use them in the search. All right, so that's the estimate cost. Now what you're going to do is you're going to make sure the tests pass. So you're going to come up here, you're going to have your student A star, you're going to click run tests. Of course, nothing is working just now, but once you have yours working, then all the tests should pass like this, and you'll hit some random tests as well. If you're super cool and you get your code to run fast, then you can come over here and you can run the tests for the Wheel of War map as well. Okay. And then if you're in 6980, what you're going to do is you're going to implement the bidirectional search. So the bidirectional search, again, that uses this variable. So if you have bidirectional selected, so over here, student A star, you'll select bidirectional. And we can see, again, what bidirectional means. So if I come over to the blank one and I hit solution, bidirectional, and I'm going to use the 0 heuristic. So this is how you should test whether or not your solution is actually working with bidirectional search as a 6980 student. Make sure you set the heuristic to 0. So what that's going to do is if you select a start and a goal, and you animate search, then what you should see is that you have 2 circles growing outward, and eventually they will meet and you'll form the path. So that's what we're going to do when we actually test your code, is we're going to set the heuristic to 0 and run it like this, and you should have 2 circles growing outward, and then eventually you find a path, and the search keeps running until you're sure that that's the optimal path. And that's how you'll know that you're going to get all the marks for 6980. And then only after everything works and you pass the tests, then come back to your open and close lists and implement the optimizations. So for example, now you can come in and insert the binary heap into the open list if you want to, or whatever other data structure that you have in mind, or you can come down here and implement a map or a matrix or whatever sort of check that or optimization that you have for the closed list. And so if you follow it in that order, and every time that you actually complete one of these steps, then you test it and you move on to the next step, then you'll always be sure where your error is, right? Because you're sure, okay, if I've completed up to here and I've tested all of this, then I know if I have an error in step 3, then it's in step 3 because I've already implemented and tested everything beforehand. And so if you follow that, even though this is a lot of work, it's a lot more programming than assignment 1, conceptually it's not that difficult. I would say that the thing that most people are going to struggle with is the compute sectors function. So again, just start it early and come to me with any questions early, and I'll be able to help you with that. And good luck. I think that this is a really fun assignment once you get it working. It's really cool. One last thing that I wanted to show in this video, because I didn't really have a chance to do it for assignment 1, was how to actually use the debugger properly within the browser. So I'm going to show this for Firefox. I'm sure the same thing exists for Chrome. You would just have to find the hotkey. But essentially, the browser has a really nice debugger built into it. So what I've done here is I've just put in some sample code here. Just let a equal 10, let b equals a plus 17, and then console.log b. So we're going to see how this actually runs in the browser, and we'll set up a breakpoint so that when our start search gets called, we can actually step through and see these variables change. So over here, I hit my Control-Shift-K to bring up the console in Firefox, but there's also another option here called Debugger. So if I click on Debugger, I get this nice little window, and I'm just going to drag this way over here to make it a little bit bigger, and I'll zoom in for you as well. And so when you click on Debugger, it may look like this, where you have main thread, and then you have to click this, and then it shows a list of all the JavaScript files and HTML files that are actually loaded in the browser right now. So the one that we're really concerned with is the search student. So if we click on search student, it will open up right here, and we can actually look at all the code that's in our file. If I scroll down here, we can see that, oh look, my code actually isn't here inside Start Search. Why is that? Let me go back and have a look. I'm going to, oh, I know why, because I didn't reload my browser. So I'm going to hit reload on the browser, and now I get that code in there. So let's say that I think that this part of the code is where I might have that error or that infinite loop, etc. And I really want to be able to step through this code to see what's going on. So over here at the line numbers, you can see how my mouse gets highlighted by these line numbers. So I can just click one of those, and then it becomes blue. So what clicking that with my left mouse button did was the same as here, is if I right click and then click add breakpoint. So if I add a breakpoint, what that means is that my code will stop running when it gets to this line, and then I can manually control how the code gets run. So I'll come back over here. I've got a breakpoint set right here. So this is inside Start Search. So what's going to happen now is when I click to start a search, the debugger has paused the execution of all the JavaScript, and so now I can come over here. So this is the debugger running, and over here I've got some controls. So if I press play or resume, then what'll happen is it will just go until the next time it reaches this breakpoint. But that won't be until I start another search, so I don't want to hit that right now. These are the things that I'm interested in over here. So this is the step over control. What that will do, it will just go to the next line of code. So if I hit step over, it executes that line of code and then goes to the next line of code. See how that works? There's another button here called step into, and what step into does is, let's say this line of code called a function, then step into would actually go into that function. And so maybe I'll show an example of that in a little bit. Then there are step out of, and what step out of will do is it will step out of this function. So it'll go to the end of this function and then start debugging at wherever this function was called. So what I want to show right now is the step over function. So I'll click step over, step over, step over, step over, and now I get to this line. So down here, what I can do is I have some scopes. So scopes, this is showing the variables that are within this local scope of the function. So over here, I can see that a is still undefined. Why? You might think, well, a is equal to 10. Well, the line that I'm currently paused on actually hasn't been executed yet. So hopefully, for the demo's sake, when I click step over, you're going to see this uninitialized a. Now it's 10. See how that worked? So I stepped over that line of code, it got executed, now I'm here. Now B is uninitialized, but I have B is going to be equal to A plus 17. So 10 plus 17, hopefully when I step over, now my B is equal to 27. So that's really cool. So that I can see my variables change in real time. Another thing over here is that the scope inside start search also has access to the this variable. So over here, I can either click this over here, or I can come over and highlight one of these variable names. If I highlight the variable name, then this down here is essentially the object that I'm currently working with, which is my search student class, which is really cool. Because here I can see all the different variables. I can see, oh look, my open list is still empty. The name is still student. The start is 29.4. The goal is 29.4. In progress is true. All of these different things. So what I can do here is I can literally, as I'm adding things to the open or the close list, I can check what all those variables are doing so that I actually can see in real time, okay, this is where my infinite loop is, etc. So, yeah, I just wanted to show you that debugger because it's incredibly useful when you're doing JavaScript programming to be able to do that. Let's do one more example here. Let's look at search iteration. Okay, so I'm going to set a breakpoint. You can't set a breakpoint at any of the lines that don't actually have code in it. So I'm going to set a breakpoint right here. And now, so what should happen is my start search function is currently being called, right? Because I've just called start search. And what's going to happen after start search is finished, it's going to then start calling search iteration. So if I hit play here, now it's given control back out to the user interface. You didn't see that though, because you didn't say step out of, you hit continue or resume. And what resume does is it goes until the next breakpoint. So here I can see that this dot in progress is equal to true. And so if it's true, then that means this whole statement is going to be false, so it won't return. So I'm going to step over this, right? This.config.bidirectional, that's false, so this won't happen, so I'll step over that. And now we can step through here. Now, this is interesting because what I'm doing here is dx is -1, this is -1, so I'm just going to step over this. That's not super interesting. What I've done here is I've tried to get a minimum f value. This is actually a good example. So my open list is currently empty, right? It has nothing in it. But what I did was I tried to get min f from that open list. However, if I go up now, get min f doesn't actually return anything. So what does that mean? It means that this node is now undefined. Because I've said, hey, this .node is equal to a function call that doesn't actually return anything. So now I can actually see that, hey, this .node is undefined. So that's a really good thing. So a lot of people had errors like that where something is undefined or trying to get X from undefined. And by doing this, you can actually see the node value. Let me do another example here where I can set a breakpoint inside my loop. So this will actually be interesting. So I'll set a breakpoint here. Now I'm going to see, okay, this.config.actions, this.config.action has a length of 8. So currently we, by default, we're set at diagonal action, so that's 8. And the reason I set a breakpoint here is because if I want to, now I can hit resume, and resume will essentially call one iteration of this loop. So I can see here that A is 3. So action is going to be this.config.actions3. And so that means that action here, oh, this line hasn't been executed yet. So now action, this is -1 in the X direction and 1 in the Y direction. So that what's that? That's like -1, that's going to be left, and 1 is going to be down. So this is the down left action. And then my cost, if I execute over that line, I could see, oh, I can't do that. Let me do that again. I'll hit here, and then my cost is going to be equal to that action cost. So you can see here inside action costs that our diagonal actions come first, and then our cardinal actions come second. Then if, for example, I wanted to go to this line of code, then I can set a breakpoint here, maybe remove this one so that then I go there. And then if I really want to, I could step out of this function, and this takes me back into the user interface where the search iteration function is actually being called. And so that's not something that you really need to know about, but don't worry about that, because that's I just wanted to show you the step out of. It's not necessary that you know this. So yeah, that's the debugger, and I hope that that very, very quick tutorial shows you the power of it and how useful it could be for debugging assignment 2.